Hello. In this two-part video, I'm going to share what I believe is sort of the vector essentials for character rigging in Houdini. That means that in this video, I will not be focused on explaining mathematical definitions and operations of vectors, but rather how vectors can be useful in character rigging and also how vectors are defined in Houdini and what kind of functions are available in VEX to help with certain vector operations. So first, let's just go quickly what vectors actually are. And vectors are defined by two pieces of information, and that is the direction, so in which direction they're pointing, and the length or the magnitude of the vector. And in Houdini we have 2, 3, and 4-dimensional vectors. So 2-dimensional vectors store 2 components, 3-dimensional vectors store 3 components, and 4-dimensional vectors store 4 components. The 2-dimensional vector is mainly used, for instance, for texture U and V coordinates. And in character rigging, we're mostly dealing with 3-dimensional vectors because we are dealing with 3D space coordinates or the positions. And we also have the 4-dimensional vectors, which in Houdini, they're mostly used as quaternions. But we're not going to cover quaternions in this video. Just know that not always, but a lot of times, vector 4, which has the addition of this W component, is used to define quaternions, which also have a rotation value. In character rigging, we're mostly dealing with 3-component vectors, which are used to define positions in 3D space. So now in Houdini, let's create a geometry node. I'm going to name this vectors and dive in. I'm going to just create a single point that we will use for visualizing all the vectors and create an attribute triangle in which here define some vectors. So in Houdini, the vector can be defined by either vector 2 or vector 4. So the vector 2 is 2-component, vector 4 is 4-component vector, and vector without any number behind it is a 3-component vector. And to define a variable, we can just define v at and the name of the variable. So this is how we define vectors in VEX. And to set values, we can use the curly brackets. So these are now the values of this vector. And if we look at here, I'm gonna just visualize this. We now have a vector, and this is the R vector, so I'm gonna just color it red. So this now tells the direction of this vector. We can also use the set function to create a vector. And the set function takes component values as the argument, and it will return a vector when providing 3 components. And if we have, for instance, a component, let's say the x component will be 0.3, we cannot use this x variable inside the curly brackets to set the vector values. We have to use it inside a function like the set function, or we can set each individual component. And to set each individual component, we can just use the .x, or for the x component, .y and .z for each individual component. And this will set only the specific component. Houdini also allows to use the RGB component. So instead of x, we can use the R for the first component, G for the second component, and B for the third component. So this is just another option, which is mainly used for setting the values of color attributes. And we can also define by the index. So for instance, the first component is the 0, second component is 1, and the third component is 2. So we can also use this kind of way of defining each individual component. So these are the options to define components and set values for vectors. Now, since in rigging we are dealing with mostly moving things around, vectors are great because we can use them to store positions and tell where things should move. So I'm going to create another add node here and an attribute triangle. If I define here two vectors, so the first one was red, and I'm going to define another one. This one will be green, and just set some values here. And just visualize these two vectors. So green. So now we have two vectors. And now if we create another vector that is the sum of red and green, and let's also visualize this one. So red, green, and blue vectors. We get the sum of red and green. And the way this works is that if we show this here, so this is our green vector. And if we add the red vector to this vector, we basically just add this component to this component here, and this is the sum of both. So if we would reverse the order of operation here, so if we add the red to green, the results will be the same, simply because if we add the green vector here to the red vector here, the result is the same. So in both cases, the blue vector is the same. However, when we subtract, this is not the case. So if we subtract the red vector from the green vector, we take the green vector, and then we reverse the direction of the red vector and add this reverse vector to the green vector. And this is now the resulting vector. Now, if we reverse this operation, the result will be different because we're subtracting the green from the red. And we can see that, actually, I'm going to draw this again. We see that we get in reverse, and this is simply because we are subtracting the green vector. So this is the reverse direction from the red vector here. That's why the result is in the other direction. So when we are adding vectors, the order of operation is not important, but when you're subtracting, the order is important. And then, since the vectors also have magnitude, we can multiply them to change the length of the vector by using scalar values. So if we multiply vectors by a float value, for instance, we change its length. So for instance, let's change this to a parameter. Like this, we see we change the length of the vector, and we can retrieve the length of the vector. So let's store this in variable L or len by using the length function, which calculates the length of the vector. And I show here the geometry spreadsheet, and here I made a mistake here. This is actually a scalar value. This is a float value. So here we see the length of this vector. We also have the normalized vector, which is basically a vector of length 1. So if we use the normalize function, which takes a vector as an argument, it will return the vector which will have the same direction, but with the magnitude or length of 1. So if we put it here, so we see the length of such normalized vector will always be 1. It doesn't change the direction, but only the length. So the length is 1. Using the normalized vectors can be very important, for instance, when using the dot product, which we will look into in the next video. So now let's take a look at a more practical example, how we can use all this here. So just by adding, subtracting, and multiplying the vectors. So a lot of times we want to know how far and in which direction certain points are relative to each other. And here we will create a very simple deformer just based on those basic concepts we saw here. So we will take a line geometry, for instance. And I'm gonna place it in the x direction. And I'm going to add, let me first just name this. So this will be add, subtract, and multiply. I'm gonna just color this a bit so we have different setups. So here I'm gonna define 2 points. Point 1, actually point 0 and point 1. And here we have our line. And actually, let's add some more points to this line. So let's add 100 points. And based on these 2 points, we will define the deformer which will deform this line. So based on which direction the second point is relative to the first point, we will define the direction of deformation. And based on the length of this vector between these 2 points, we'll define the magnitude of this deformation on this line. So we will create sort of this deformer that moves the points in a specific direction based on these 2 points. So let's create an attribute triangle now. And connect the first input to line. The second input will be used for these 2 points. And this will be, let's call it simple deformer. So now we need to find the position of these 2 points here. And this will be position of the first point. And we can get the position by using the point function. Point index 1 will be from the second, means that it is the second input. And we're interested in the position. And this is our position vector. We can do the same for the second point. I'm going to just copy this code here and change it to read the position of point number 1. And now we have 2 vectors that we can use to define the direction. So if we subtract, we now have a direction. Actually, I'm gonna just maybe store this in an R vector, so we just see where the direction vector is. So as you can see, based on this one, we are defining the direction in which the deformation will take place. So this is now our direction vector. And we also define the magnitude, how much this line should be deformed. So as we've seen in a previous example, we can just use the length, or in this case, let's define it as magnitude, how much of the deformation will be applied, and this will be based on the length of this vector. And now let's also define the position vector of the current point, which is simply the position variable. So now we will want to define how far from the first point. So the first point is here. And I'm going to put this point here on this line. How far away from this point we want to deform these points. So we only want these points very near or far away. So let's define the effect distance variable, and we will define this as a parameter. So for now, let's set it to something like 0.5. And then we can simply define another vector, which is just the distance between the position of this point here and each individual point on this line. So the c distance is now length of vector c. And if distance is lesser than this effect distance, we can say that the position is the position plus this vector d. Actually, this mistakes, which here should be c distance. And now we can see we are deforming the line points based on these two point positions that we defined here in this add node. Okay, so even though our deformer basically works, let's just update it a bit so we get a better slope and use little wicks to our advantage here. So what we want is a smoother fall off towards the edge of the formation. And here we can use a fit function which will remap the affected distance into 0 to 1 range. And then we can, for instance, use a ramp to define the slope or the fall off towards the edges. So what we will do here is just calculate the new affected magnitude, which will be a remapped magnitude. And first we will take the c distance and remap it between 0 and the affected distance and remap it into the range of 1 to 0. So when the point is closest to this point, the magnitude will be the highest, and when the distance between this point and the actual point on the line will be closer to affected distance, it will slowly fall towards 0. And now we can just remap using the ramp parameter. Let's call it remap. This will be affected ramp. So now we get this kind of parameter, and let's just set it to smooth. And then we can just multiply the deformation direction vector by this affected magnitude. So now we have this sort of effect, and we are using just these vectors to define the direction and magnitude of this deformation. So this is a simple example how using basic vector operations such as adding, subtracting, and using the vector magnitude or length to move points around. And all these operations are sort of the basic or fundamental part of almost any kind of geometry deformation. We can also multiply vector with another vector. And in rigging, this can be useful, especially when we would like to mirror across an axis, for instance. So let's create another line here. Again, x direction. And let's create 11 points. And I'm going to set the origin to minus 0.5 and the length of 1. So what we get here is the same number of points on left and right side of the x-axis, or should I say in the negative and positive side of the x-axis. And I'm gonna add point jitter And I'll set this just for the points on the negative side of the x-axis. The scale is too much. Let's do something like this, for instance. And what we want to do is mirror across the x-axis, so we have the same effect on the right side. So this is very common in character rigging, where we have to mirror across an axis. So we will again use the attribute triangle and call this one mirror. And we will only mirror these points here. Now, first we'll need the position, which will simply be the P attribute. And then we will define the vector, which will define the axis across which we will mirror. So this will be a multiply vector. So each component of this position will be multiplied by this vector. So if we set this to -1, 1, we will get the position of each this point on the other side. So we can now define the mirror position or the mirror vector. So this will be simply position multiplied by the axis multiply vector. And basically what we're doing, we're just multiplying each component to each component. So position x is multiplied by -1, position y with 1, and position z with 1. This way we get the positions on the other side. And then on this side, we'll do one more thing here. We're going to connect the second input to this line before the deformation. So right now they are symmetrical, which means that we can find the mirror point by using the near point function from the second input. So it's from this input using this mirror position. So that means that here for point 6 we'll find point 4, point 7 we'll find point 3, and so on. And now we just have to find how much each of these points has moved from its default position, or from how much the point jitter has moved points around. So again, we'll just define the offset vector. And we will take the vector, which is now this position, and subtract the default position. So that means that each of these points will return a vector like this. So for each of these points, we'll get this kind of vectors, but here on this side. So if we visualize this here, and say the red vector is offset we get now this kind of positions. Okay, so this one has moved here, this one has been moved here, as you can see, this one has been moved here, and so on. So now we can move the point, the position, plus this offset position. But as we can see, we also have to mirror back this mirror axis. So if one point has been moved in the negative x, on this side here, it should move in the positive x. So that means that again, we have to use the multiplication. So the axis multiplied multiplication, so we get the negative offset. And now, let's hide this, we see we get the mirroring effect across the x-axis. So as you can see, just by multiplying the x component of the vector, we can start using vectors for mirror operations, for instance. And that's it for part 1. And in part 2, we will look into the vector dot product and cross product.